Hi there, this is Math 8, Unit 2, Lesson 8. Today you were talking about similar triangles in class. And so you began by just having some conversations about making, first of all, some pasta and turning the pasta into angles and triangles. And so in class, what your teacher gave you was some dried pasta and a set of angle measurements. And you took those pasta pieces, whatever they might be, and you laid them out to make for yourself some angle measurements based upon what they gave you, and to create yourself a series of pasta-shaped triangles or triangle-shaped pasta pieces, whatever you want to say. Anyways, so we played with that a little bit there, and then you walked around the room to share with other people who had the same angle there, and you did some comparisons, noticing what was same, what was different, talking about congruency and similarity there, looking at your different triangles. Okay, it's just kind of a little fun activity. I'm not going to recreate that for you there. If you kind of moved around there, you talked about some more, tried to make other angles, and you played a lot of pasta. This one here I'll talk about real quick as kind of a recap. It says here's triangle PQR, break a new piece of pasta, different length and segment PQ. So let's say, for example, I took a piece of pasta and I made it like this long right there. Or maybe I made it a little shorter. So I made a piece of pasta maybe this long, okay? And then tape a piece of pasta so it lays on top of PQ. So if I had a piece of pasta this long, from there to there, okay, and at P, and then label the other end S, we'll label that S, and then tape a full piece of pasta one at S, making an angle congruent to PQR. So we're going to recreate this angle there, meaning if this was like, I don't know, 35 degrees or something, we would make another line like there with another piece of pasta. Trying to make a congruent angle was the idea, here to here. And then we go ahead and we connect the top there, and what we end up with, we call that point T, you end up with two triangles, almost looking like a dilation there, right? Where this one is here, and that one becomes almost like a dilation as it grows out that direction there. But what we end up with is we have one common angle here, and then these two angles are identical to one another. So when we talk about this triangle, one of the questions is your new pasta triangle PST similar to PQR? So that's the question, is PST, question is PST similar to triangle PQR? That's the question. And we would end up saying, yeah, they are similar, because with a triangle, the sum of the angles in a triangle is going to be 180 degrees, right? So if we know two of the angle measurements are exactly the same, if we know that A plus B equals A plus B, and they all add up to 180, we know we're in good shape here, okay? So as long as we have two congruent angles, we're going to end up with, that means if we have two congruent angles, then the third angle is also congruent, okay? And that's what we're looking at there. This is part A there. If you broke the broken piece of pasta for a different length, would the pasta triangle still be similar to PQR? Meaning, if I had the pasta broken right here and did that, would it still be similar? Yep, it would still be similar. As long as this is going to be the same angle measurement there, we're going to have similar triangles. Okay, so that's what we're working on there. And then the next thing you took a look at is we had a diagram in 8.3 of several triangles that are similar to DJI. So DJI is right here in this space, right there. There's DJI, and that's where our triangle began. Now for that triangle, what they're asking us to do is they're saying, okay, this says three different scale factors were used to make triangles similar to DJI in the diagram. Find at least one triangle of each size that is similar to DJI. So we're going to be looking for three different triangles that are similar to DJI. Now there's a couple ways of doing this here. I could take a look at the triangle itself, and I can just trace this guy out just to begin with, just to show you what we're doing. Trace this out, and we notice that we have angles, angles, and this one's different. This looks like an isosceles triangle, doesn't it? Okay, so that's my triangle there. What we've been talking about is that if I have two angles that are congruent, then the third is 2, and then the triangles are going to be congruent. That's the idea for what we're talking about. So if I know the triangle angle measurements are congruent, we're going to be in good shape. One of the first ones I noticed was that this triangle can be extended all the way down to there, can't it? All right, here to here to here. We call that triangle DAB, the larger one. If it's true that it's congruent, then our angle measurement should slide in place there. And when we drop this little triangle, our initial one on top, we have the same angle there. We have the same angle measurement there. And of course, the top one's the same angle measurement there. In terms of a scale factor, or what that's going to be as a length of some sort, what we might be able to do, because we want to say it larger or smaller, we could take a look at our initial one. We could plot this off and say I started about here and went to there, and we notice that we're going to there is times 2 and there is about a half, so it's probably about a scale factor of 2.5 from the original is what's happening with triangle DAB. Okay, that's one triangle right there. I also have another triangle. If I look at it, maybe it's a little tricky to see, we want it to be similar. If I look right here in this shape, I have one that's upside down. So let's take our little tracing here and let's see if the angle measurements are going to be the same. When I slide it in the position here, we see that that angle is the same, and then our bottom angles are also the same. As a result, we would say that triangle BCI is also congruent to triangle DJI. Okay, so in this case here, talking about scale factor again, right? How do we get there? If this is my length of 1, notice that my length of 1 goes 1 to there, and then again another about a half, right? So it's about 1.5. So our scale factor is about 1.5 in terms of how much larger this one is from the original. Okay, and one of the other things we want to talk about and look at today is that you do have other triangles. This is where you might get stuck. That's one solution. Here's another solution. The third solution is maybe where you might get stuck a little bit. But don't worry about it too much. It's not too hard. Look at this. We have another triangle right there, don't we? That triangle in this case is the same as that one. Triangle, we would say CIH, is also congruent to this one here. So what's the scale factor moving from here to there? We would say in this case here, our scale factor is simply 1. Even though it is a different triangle, has the same scale factor, it's all going to be good. So in this case here, there are 3 different triangles that are all congruent to what we started with, right? We had our initial one here, which was located right there. We have our larger one, which was here. That's our larger one, okay? And then we had our upside down one here, which is also congruent. And then we had our one to the side. I used that one, but I could also use one over here if I wanted to just make it a little cleaner. Same idea. Okay, so those are 3 different triangles that all have they are similar to our original one, and they have a different scale factor, either 2.5, 1.5, or 1. And the reason we know, question B, that these are all similar is because they have the same angle measurements, don't they? And when they have the same angle measurements, they're going to be congruent triangles. And that's the key thing there. Okay. So, moving on to our next part here. It says, figure out how to draw some more lines in pentagon to diagram to make more triangles similar to over here. Find a triangle diagram that's not similar to DJI. If I'm going to find one not similar, then that means I'm looking for a triangle that's in there but doesn't quite have those same angle measurements. And so you might look here, for example. Here's one there. That triangle right there is not similar to this one. The angle measurements won't fit in there at all, so I can't make it work. And so that's just one example of a triangle that's going to be different. In this case here, triangle EDA is not congruent to our original one there. When it talks about can you draw some more triangles in here to make some more similar shapes, you could. Kind of fun way to do it if I connect some dots in the middle. Connect some dots, and connect the dots, and connect the dots, and connect the dots. Now I have even smaller triangles, and once again, if I was to check this out, I'm going to have the same angle measurement at the top, the same on the base, and same on the base. So this small triangle right here would be congruent to our other one as well. Kind of fun to play with. So as a summary, today's lesson says that we learned earlier that two polygons are similar when there's a sequence of translations, rotations, reflections, and dilations taking one polygon to the other. When the polygons are triangles, we only need to check that both triangles have two corresponding angles to show they are similar. All we need are two corresponding angles to show that they are similar, right? So if we had an example here, a triangle, where we have a 30-degree right there, right? And I have a 30-degree right here. There we are. If I know a 30 is a 30, and I know the other is a 45 and a 45, as long as I know that there are two, then I can say that these are going to be similar triangles. And the way we do that is we take our small one here and we translate it so that A lines up at point D, right? And then when we take a look, our line ends up with a triangle like this. We have a small one inside of a larger one there, and this is still our 30s there, and this is still our 45 here, and this is the other 45 there. Okay? And again, just to kind of show mathematically how this works, if we had a 45 and a 30 all together, that's 75 degrees that we've used up inside the triangle. What's left out of the 75 is going to be 180 minus 75, which is going to be 105 degrees. So I have 105 degrees left here, and I also have 105 degrees left there. So these are going to be similar triangles. And we can prove that with a rotation and a dilation to make sure that this is going to be two congruent or two similar triangles because they have two congruent angles. That's all we need. If we have two, then the third is 2. Have 2, the third is 2. All right, so take a moment to pause there, work on your homework a bit, and then press play, and we'll resume. And see how you've done your homework. Okay, so here's the homework for lesson 8. All right, in each pair, sum of the angles of two triangles in degrees are given. Use the information to decide if the triangles are similar or not, and explain how you know. And again, I'll show you kind of how they are, but you have to write off explaining how you know. When I look at triangle A and B, our goal, remember, we want to have two angles the same. That's our goal. We want to find two angles that are the same in order to prove it's similar. So in this case, I have 53, 53, 71, 71. Do I have two angles that are similar? Yep. So I have two congruent, write it like this, equals with a little squiggy, two congruent angles. And that's how I know that that's going to be similar there. For this one, I have a 90 and a 90. That looks good. And you might say, well, 37 and 53, those do not match. Well, you'd be right there. Let's see what happens if I find out what's missing. Let's use D. If I did 90 plus 53, then I have 143. That means I've used up 143 out of the 180 degrees possible inside of a triangle. Okay? So when I subtract what's left, I end up with 10 minus 3 is 7, and 7 minus 4 is 37. My other angle measurement here is going to be 37 degrees. Well, does that match what I have? It sure does. And so I have two matching angles. So again, two congruent angles is why they're going to be similar triangles. Okay, took a little extra step there, but you can certainly get there, no problem. Sorry, zoom in a little bit there. Didn't realize that was so far out. For this next one, I have a 63 and no 63. I have a 45 and no 45. So nothing matches at all. I can't even see if those are the same or not. They could be, but it doesn't matter because I don't have anything similar. So we would say no to that one there. On this one, it's not really going to work out either because let's say, first of all, if we knew what those could be, I want to try to find two that match. Those two are going to have to match. But if those two are going to have to match, then I'm going to have to still combine 121 with 70. Let's say 70 was there and 121 was there. Well, that's already 191 degrees. It can't be greater than 180. So there's no possible way that's going to work. It's just not going to work out too well. Okay? For number 2, you're going to draw 2 equilateral triangles that are not congruent. Now, by not congruent, that means they're going to have different side lengths. The angles are going to be the same, right? So 3 angles are going to be congruent, but the side lengths will be different. So equilateral means it's going to have 60-degree angles inside of it. So you might draw, and this is just me sketching here, okay? You might draw one like that, right? Perhaps about 60 degrees, but you could also draw a smaller one, and those would not be congruent. They are similar, but not congruent, because they're a different size. Congruent is going to mean that they're going to be equal in the size, the shape, and the lengths, everything. Those would not be considered congruent triangles. They would just be similar. Okay, measure the side lengths and angles of your triangles. Are the 2 triangles similar? And again, we just talked that through. We would say yes, they are. Our angles are congruent, but our sides are similar. We're probably going to find a proportional relationship here. This, for example, might be 1 centimeter, and this one could be about 3 centimeters. So I have a 3 by 3 by 3 and a 1 by 1 by 1. So they are related, but that just means they're similar, not congruent. C, do you think 2 equilateral triangles will be similar always, sometimes, or never, and explain your reasoning? If we're talking about similarity, I would go with always similar. And the reason for that is, right, the reason for that's going to be they have 3 angles that are congruent. Therefore, we have similar triangles. Okay, so we're going to say there's 3 angles that are congruent, which will make us say that they're going to be similar triangles. All right. All right, in the figure, the next figure, BC is parallel to line DE. Let's take a look here. BC is parallel to DE here. So this line, draw a little arrow there, is parallel to this line. Okay, or if we thought about what we did in previous lessons, we would say this line is parallel to this line there. That's our parallel line. We've talked before about parallel lines. We've also talked about things we call transversals, right? So here we have a transversal. All right, it comes up again and again. What do you know? Okay, explain why triangle ABC, the large one, is similar to the small one. Why would those be similar? Some things you want to talk about as you write your answer. We have a common angle there they both share, right? So triangle, so measurement of angle BA, the middle one is A, BAC is equal to the measurement of angle DAE. So this angle equals that angle. Okay? We could also say that angle AED is congruent to angle ACB. Right? So this one here, 2 lines, is there. Now the reason for that is that because we have a transversal here, these angle measurements are going to be equal to one another. The parallel lines with one transversal is going to result in angle measurements that are the same. Now that we know that 2 angles are congruent, therefore the third is 2, so our triangles are going to be congruent to one another. That's the idea. I made a kind of short form of how to explain that there. You'd want to do it in your own words, how you'd write that out. Okay. The quadrant of PQRS in the diagram is a parallelogram. Let P prime, Q prime, R prime, S prime be the image of PQRS after applying a dilation centered at a point O, not shown, with a scale factor of 3. Which of the following is true? Okay, so what I did here, just thinking about it, thought, well, it's not shown. Let's just see what happens if I made up a point. What if I called this O, just to see, okay? And I did a scale factor of 3. If I called that O, then my P prime would be, if this is 1, 2 away, then 2 times 3 is going to be 6 away. So my P prime would be 6 away. So we'd have 2, 3, 4, 5, 6. So there's where P prime might be. And for Q, I went down 1, 2, and we go 3, 4, 5, come off the grid here a little bit. 6 for q prime. Okay, so that's kind of where I'm hanging out there, which means that my line to connect those two, my p prime, q prime, will be something like this. Okay, so just using that as a guide. You didn't have to do that, but to help you visually see it here. Is the length of p prime, q prime equal to pq? We'd say no. This has a length of 2, this has a length of 1, 2, 3, 4, 5, 6, right? So they're not going to be equal. Is the length of this equal to 3 of those? Well, if this was 2, and we just measured this as being 6, is 6 equal to 3 times 2? Yes, it is. So we're going to go with, yep, that would work. Is this one equal to 3 of those? Is 2 equal to 3 times 6? Nope, it's not. So that's not going to work. And they cannot be determined. Well, we can determine one thing. We can determine B. So we're going to go with B being okay. All right. Number 5, describe a sequence of transformations for which quadrilateral P is the image of quadrilateral Q. So how do you go from Q to P is what we're trying to do. Trying to move from one to the other. So a couple different ways you might do this. You could begin with, first of all, perhaps a rotation. Okay. So, and again, there's lots of ways to do this. Maybe you rotate 90 degrees counterclockwise at point 7, -4. So we make this our middle point here. So we're going to pivot around that point right there. By doing that, this is going to become 1, 2, 3 long. 1, 2, 3 long. We go out 1, and then we're going to go diagonal. We're going to go 2. We're going to go 1, 2, 1, 2, 3, 4, 5. So just can't see it in here. 1, 2, 1, 2, 3, 4, 5. All right. I think that's right. Looks fun. Let's double check it. Tracing paper. Sorry. It's been a long day already. It's only the morning. So we're going to go there. We're going to pivot. Rotate 90 degrees counterclockwise and land right there. That's what I wanted. Okay, so this point's going to be here on this line. So I connect it there and I connect it there. This is only step 1, right? So step 1, we rotate 90 degrees counterclockwise to get there. And then we want to translate, and we're going to go up 1, 2, 3, 4, 5. Translate up 5, and we're going to translate left, since we end up being here, 1, 2, 3. So translate up 5 units and translate left 3 units in order to get that in the right place, so we land right on top of that. So we started here, rotate 90, translate up, and then slide to the left. Okay, and that's how you get that. Hope you have a great day, and we'll see you next time.